Alright, so we are in the second lecture of the first module. In the first module we are covering the fundamentals that will be required for building various things for the rest of this course. It's some kind of a recap of past concepts that you might have done in your undergraduate, but essentially I am going to start at the basic level and then rebuild those concepts again from top down rather than bottom up. Okay, but again we are just going to recap a few things. Before we do that, let us talk about what all we have done so far. Okay, we have talked about various types of reactions. Okay. We took a couple of examples. One was ammonia decomposition or ammonia synthesis, and the other was propane combustion. And we also very briefly would be less than half a minute, saw other type of mechanisms that would be gas phase reactions as well as gas surface reactions. Okay, so let us talk about the ammonia. This is what we balanced it as. Okay. If the reaction is reversible, we show this in this particular manner. Okay, with a double sided arrow. You can show it like this, you can show it with an arrow like this, really that does not matter. Okay. Now, in general all reactions are under equilibrium. Okay, even a combustion reaction is under equilibrium. So, if you look at a reaction of the nature CH4 plus O2 giving CO2 plus H2O, okay, that also is an equilibrium reaction. The reason why we show it with unidirectional arrow is because the Kp of that equilibrium is of the order of 10 to the power 80. Okay. That means if the reactants and products are under equilibrium, you can take pretty much all the molecules of CO2 and water that might be present in the universe, you will hardly get even a single molecule of methane and O2, maybe a couple of molecules. Okay, that is how much the reaction is towards the right hand side. Okay, but you do have CO2 fixation, right? You do have plants that take up energy, and from CO2 they go on to form carbohydrates. From carbohydrates, when the plants might have died and they might have gotten buried under the soil, those carbohydrates might have gotten converted into coal and oil and methane gas as well. So, that reaction has taken place in the reverse direction, though not necessarily in the same way, not necessarily in this direct pathway. Indirectly, it can go from here photosynthesis to form carbohydrates, and from carbohydrates, and then photosynthesis can lead to formation of oxygen, and from carbohydrates you will get to carbon plus oil plus natural gas. And natural gas, an important component of natural gas is indeed this. Okay. So, this can very well happen. If it were truly irreversible, the backward thing would not be possible. Okay. You know from thermodynamics that enthalpy, for example, is a state function, entropy is a state function, free energy is a state function. What that means is that the delta G, delta H, delta S are independent of the path followed, they are only dependent on the initial and final states, right. So, yes, you can go from CO2 to water, from CO2 plus water to methane plus O2. In fact, we can do it catalytically also. From water, or you can generate hydrogen. With hydrogen and CO2, you can react in a reaction called Sabatier reaction in order to get CH4, right. CO plus H2 to give CH4, you have already studied it as what? Methane synthesis reaction. It is a reverse of reforming reaction. right? CO2 plus H2 giving CO plus H2O. What's that reaction called? Water gas shift, right? Actually reverse water gas shift, right? So these are reactions that you have studied. They can very well happen. They won't happen spontaneously. Okay. Okay. So now when we talk about reactions, we then talked about balancing these. We spoke about stoichiometric coefficients. Okay. And again, in your undergraduate or high school, you might have looked at a reaction of the form AA plus BB giving CC plus DD, and for this you might have studied RA divided by minus A equal to RB divided by minus B equal to RC divided by C equal to RD divided by D, right. Okay. This is what I am going to represent as rate of progress of a reaction. Okay. Really it is rate of reaction, but in order to avoid potential confusion with different terminologies that you might have used in your various different undergraduate programs, I will just call it rate of progress of reaction. Okay. It is basically the rate of change of moles per unit volume per unit time, okay, as the reaction is written. Okay. And if there is only one reaction taking place, your RA is minus A multiplied by R, your RB is minus B multiplied by R, your RC is C multiplied by R, your RD is D multiplied by R, right. Now recall that we had said that capital R A is, or capital R K okay. If there is only one reaction, you are basically going to get capital R A if only one reaction, right. So nu Kj is nothing but minus A, Rj is nothing but R, and when you write it together you have R capital R A equal to minus A multiplied by R. Okay. So your undergraduate minus R A okay. This is the only time I am going to use the notation small r a, okay. The notation small r, I am going to reserve it for rate of a particular reaction. The notation capital R, I am going to reserve it for rate of progress of a rate of formation of any species. Sign convention, if capital R is positive, the species is being formed, that means that species is a product. If capital R is negative, the species is being consumed, which means it is a reactant. Okay. Small r being positive means the reaction is progressing from left to right, small r being negative means the reaction is progressing from right to left. Okay. So, this is the slide from the previous class, okay, and we are going to define different rates of reaction, the rate of reaction per unit volume. I am going to represent it as Rj, rate of reaction per unit time per unit volume, rate of reaction per unit time per unit surface area. I am going to define as minus Rj dash or Rj dash, sorry, not minus, and per unit mass I am going to represent this as Rj double dash. Okay. This is a notation, these are the notations that I will consistently use throughout this course. Again, just to finish off our definitions of rate of reactions, I will, before that I will just talk about intensive versus extensive properties. Okay, before preparing for all of these lectures, okay, pretty much lectures for this first module with the exception of transport, everything else I am looking at up to 12th standard material. Okay, so the terminologies that I am using, I try to use it from Chem Libre text for material that is covered from pretty much 5th standard to 12th standard. Okay. Why I am doing that is because that is one baseline that I can be very confident of, it is common between everyone. Okay. Thereafter you might have branched off into different undergraduate curriculum. Okay. This is not to say that you have not learnt and things like that, but that is a common point for all of you. Okay. So, all my terminologies, all my development is starting from that particular perspective, but assuming that under different conditions you have heard all of these terms. So, you are familiar with those terms, but you might have forgotten, or chemists amongst us, or energy engineering amongst us, or biotechnology people amongst us would have covered these materials quite differently than chemical engineers might have covered. Okay. So, that is the assumptions and baselining that I am doing. Okay. What do you understand by intensive properties? Does not depend on the amount of substance. Example of an intensive property: temperature, what else? Density, viscosity. What is example of extensive property? What else? Energy, let us call it enthalpy, entropy. Okay. What about concentration? Intensive, extensive? Intensive. Why intensive? You take this box, split it into two, concentration here, assuming well mixed box, concentration here remains the same. Okay. You take this box, split it into two, M1 plus M2 is going to be equal to the original M. So, extensive versus intensive. Rate of reaction, intensive. Rate of reaction is an intensive property. Okay. Rate of reaction is defined per unit volume, per unit surface area, or per unit mass. Okay. So, if again assuming it is a well mixed system, you take that entire dabba, you cut into a half, the rate of reaction remains the same. Okay. And the reason lot of times for our confusion with our IUPAC definition is because we think naturally about rate of reaction in extensive terms, because we think about it in change in number of moles. Number of moles is extensive. Its change in number of moles per unit time is extensive. Divide it by unit volume, it becomes intensive. Total number of moles is extensive, mole divided by volume, concentration is intensive. Mass is extensive, mass divided by volume is intensive. Okay. The other reason for confusion about rate of reaction is because rate of reaction is really, the reaction is really happening at a molecular level, but whatever we are measuring it at bulk level, and then we are trying to correlate what we are measuring at bulk level to what is happening at an individual level. Okay. And that is the reason why sometimes when it comes to the rate of reaction, there is a little bit of confusion. Okay. Now, when it comes to rate of reaction, we will give constitutive relation, or also known as rate law. If it is power law, and so on. Okay. In general, we might represent this as K, okay, or we might have more complex in catalysis, Langmuir-Hinchelwood. We might have things like Michaelis-Menten when it comes to enzymatic reaction, and so on, and options are endless. Okay. This is what we are going to cover in module 2. This is in module 3. This is in module 4. Okay. We are going to come to that in subsequent modules. Yes. Yes. They are related to each other. Anyone going to answer that? Is rate of reaction and rate of reaction related to particular component, are they same or different? Anyone? Not necessarily. If you start talking about it from a quantum chemical perspective, not really. Yeah, but yes, absolutely, you can do it that way. Yes. But can you answer his question? How are they two related? They are related with respect to stoichiometric coefficient. Okay. The definition that undergraduate textbooks use, okay, is with respect to the primary component. We call that primary component A. Okay. How do we rewrite? We rewrite the reaction in this particular form, right. Look at the stoichiometric coefficient of A. We always rewrite in terms of the stoichiometric coefficient of A to be -1, right, and therefore there is a statement in several undergraduate books is that the rate of reaction defined in this manner is independent of how you write the reaction. Okay, it is not really independent of how you write the reaction, because you have rewritten the reaction such that the stoichiometric coefficient of A is -1. Okay. So, therefore, when you write a reaction in this form, your small Ra is going to be equal to -1 multiplied by small r. Okay. Gets confusing, right? Now, if you have a reaction that is elementary reaction, which is 2A going to A2, NO plus NO going to N2O4, that is an elementary reaction. That means rate of that reaction is K multiplied by concentration of NO squared. You cannot write the elementary reaction as NO going to half N2O4. NO going to half N2O4 is no longer elementary. If you already have a beautiful elementary reaction, why would you ever want to write it in a non-elementary form? Okay, except for convenience of this particular notation. Other than that, you will never write an elementary reaction in a non-elementary form. Okay, because if you write an elementary reaction in an elementary form, your kinetics, thermodynamics and your quantum chemistry all line up very nicely. When you do not write it in those forms, you need to do mathematical jugglery to get them to line up. Okay. So, if you have an elementary reaction, you always write it in that form. Okay. Again, these are nuances that are not covered in your undergraduate because it is not really required, that is one. Second thing that happens in undergraduate is those assumptions are usually put in chapters 1 and 2, and then you go on for the rest of the semester, and we usually do not get time to go back, you know, to the first 3-4 lectures of the course to revisit the assumptions that are made. Okay. So, instead what we are going to do is we are not going to confuse ourselves by using the terminology small a, small r a, small r b, small r c, small r d. Okay, very much valid terminology, but we are not going to confuse ourselves using that. Rather than that, small r, I am going to reserve it for the rate of reaction as it is written, and capital R is I am going to use it for rate of formation of a species, and we will let the sign convention take care of whether the reaction is in forward direction, reverse direction, whether it is a reactant, whether it is a product. If you have, you know, sequential parallel reactions, it might still be, you know, simple to analyze, but what if you have a network of reactions? Suddenly it becomes very, very complex because the same species might be reactant as well as a product. Okay, and Gauri is here. No. So, Gauri in her experiments where she is looking at possibly oxidative dehydrogenation as well as reforming reaction taking place together. Okay. There is one reactant which is an alkane, which is definitely a reactant, but everything else can be a reactant or a product depending on context. At lower temperatures it might become a reactant, at higher temperatures it might become a product. So, something that we have added as a reactant, at higher temperature there is more of the reactant coming out of the reactor than we have added. Okay. Why does that happen? That happens because the catalyst has a property of storing oxygen. Okay. All of those complications are not something that you are exposed to in your undergraduate. So, some of those things, that the assumptions that we make in our undergraduates make it a little bit difficult to apply these concepts, at least in my research, and I can speak about that for Professor Jitin, Professor Preeti, Professor Sagar, all of their research. It becomes very, very difficult if we really stick to those fundamentals. Okay. So, what I am doing in this course is cast a broader net, show you a broader picture, and then if you want to, you know, simplify it in this particular form, you can absolutely simplify it in this form because you find your undergraduate type of way of thinking convenient, but this is valid only in specific cases. The development that we are going to do is more general. Okay. So, yeah. Okay, any questions? Let's have a break for maybe a couple of minutes. We had yesterday we had said that zeta equal to 5 moles. Okay, let's say the reaction takes place uniformly over say 20 minutes. Reaction takes uniformly over 20 minutes. Let me just right. This is what we did yesterday. Okay, let us say zeta equal to 5 happened over say 20 minutes. Okay, in a 1 liter constant volume vessel. Okay, the rate of reaction, okay, is going to be 1 by V sorry final of 5, yes, thank you. Okay, so this is small r. What is capital R into equal to minus 1 multiplied by okay, fair enough. Now, the example that I had given from my research was about ammonia decomposition. Okay, so somewhere using solar energy or something, someone had converted nitrogen and hydrogen into ammonia, and ammonia was stored. You took that ammonia on let us say a vehicle and then converted back ammonia back into N2 plus H2. Okay. So, let us consider ammonia decomposition reaction. Okay. Let us say that we did not know it was ammonia decomposition, and therefore, we had written this as N2 plus 3H2 giving NH3, 2NH3. Let us say we started off with 0, 0, 25. Let us say zeta was negative 10, let us call it. Okay. So, final is going to be 10 or whatever formed is going to be minus 1 multiplied by minus 10, so 10 minus 3 multiplied by minus 10, 30, 2 multiplied by minus 10, so it is going to be minus 20. Final is going to be 10, 30 and 5. Okay. Small r, and again assuming that the same reaction took place in a 1 liter vessel over 20 minute period, we will have 1 by V delta zeta by delta T, okay, sorry, not equal to, approximately equal to, and this approximation can be very wrong. If your time period is probably 20, this approximation does not hold, right. D by dt is approximately equal to delta by delta T if delta T is tending to 0. In 20 minutes probably is not tending to 0, okay, unless you are talking about very slow reactions, you know, say photosynthetic reactions, some of them can be really slow, yeah, but most reactions of our interest are not slow enough for this approximation to be valid, but let us say it is valid, okay. This is 1 divided by 1 minus 10 divided by 20 equal to minus 0.5, okay. So, for the blue case your R N2 is minus 1 multiplied by minus 0.5, that is equal to 0.5. RH2 is 1.5, okay, and this is perfectly valid. We have written the reaction as N2 plus 3H2 gives NH3. That same reaction can be used whether the reaction is taking place from left to right or whether the reaction is taking place from right to left. Why? What takes care of it? The sign convention. If the reaction is progressing in this direction, that value is positive. It is progressing in opposite direction, that value is negative. Okay. If you are confused, do not worry about the blue part, only think about the red part. Okay. If you are not confused, yeah, you can look at both blue and red. Okay. But if you are only going to think that the reaction is going to proceed only from left to right, you are in for surprises, as we do have reversible reactions taking place, okay, and reversible reaction can also happen from right to left, okay, but we do not need to come up with an entire new formalism to handle that. The same concepts that we have learnt are very much applicable, just with negative sign, okay. No, this is even more confusing. Okay, we will have a tutorial problem on this next week, so that it will get clear. Okay. So, whenever we do want to develop model equations, okay, the model equations, there are two parts to it, okay. One is overall balances and other is constitutive laws. Constitutive laws would be, for example, liquid volume does not change with temperature, that is a constitutive law. Is it true? No, it is not exactly valid. We have equations of states to capture liquids as well, but for the most part, for the temperature changes that we are looking at, under the pressure conditions that we are looking at, it is valid. If we are going to look at reactions such as underground coal gasification, not really valid. If you are going to look at reactions that take place at 100 bar pressures, not really valid, but for 95% of the cases it is valid, okay. So, what is the constitutive relation for liquids? V equal to constant. What is the constitutive relation for gases? If it is ideal gas, PV equal to nRT, Okay. If these are non-ideal fluids, they will be replaced by equation of states. Rate of reaction is kCa to the power 0.15, that is a power law kinetics, that is also a constitutive relation. Constitutive relations is, there is an expression on the right hand side, you plug in the values in that expression, what you get is a result. That result is the value of rate of reaction, of volume, pressure, whatever it might be, diffusion, diffusivity, all of that, those are all comes under constitutive relation. A majority of your time as undergraduates, most engineers, especially chemical engineers, would have spent on the other type of equations, those are called balance equations. Balance equations are mass balance, energy balance, species balance, momentum balance and so on. Okay. All of the balance equations follow the same format. The rate of accumulation of any conserved quantity is going to be equal to rate in minus rate out plus rate of generation. Okay. So, let us look at the overall mass. Okay. Rate of accumulation will be always written in terms of d by dt of that extensive quantity. Okay. Most of the cases that you have seen, this extensive quantity will be written in terms of some intensive quantity multiplied by volume or some intensive quantity multiplied by mass. Okay. So, if it is total mass, it is going to be written as rho, that is density, that is mass per unit volume multiplied by volume. Okay. Rate in would be rho in Q in minus rho out Q out, or in terms of, we will call it m dot in minus m dot out. Okay. Or this will be in terms of m dot product with n bar, it is an outward going normal. Okay. This is what you would have done in your mass transfer or your reaction engineering. This is what you would have done in your transport phenomena course. Okay. They are essentially equivalent. Okay. M dot is the total mass flow. Okay. If it is coming in, it will be negative value, because n bar is outward going normal. If m is going out, okay, its dot product with n bar is going to be equal to 1, and you will have q out multiplied by rho out with a negative sign. If it is coming in, the outward going normal is in this direction, it is coming in this direction, your dot product is going to be negative 1. Okay. So, essentially the things that you have done in transport, in mass transfer, heat transfer or any of your engineering courses are essentially exactly the same. Okay. The difference is, where did we form this control volume? Okay. Rate of generation in a CRE course, this is most often due to reaction. Okay, we will come to that later. Okay, when gas liquid reactions and so on. As far as we are concerned right now, we can just look at reaction. Okay. Rate of reaction will be the constitutive law, and we are going to spend 3 to 3.5 weeks on various different constitutive laws to get rate of reaction. Okay. These are the things that we can focus on. Okay. Now, this rate in that we are talking about is only because of the net transport or convective transport or advective transport, but there is also the diffusive part. The diffusive part will just represent this as J, okay. And then there will be another constitutive law, let us say Fick's law, okay, or Fourier's law, that will take care of that. We will come to some of these things, the differential aspect of it 2 days, 3 days from now. For now, we will look at basically the overall integral behavior, okay. Let us talk about a well mixed reactor, any intensive variable. So, you just replace okay, where phi could be momentum and that will lead to momentum balance. Your phi could be partial molar enthalpy, that will lead to energy balance. Your phi could be your density, that will lead to the overall continuity equation, or the phi could be species mass fraction and that will lead to species balance, okay. We will come to this 2 days from now, okay, probably Tuesday or Wednesday's class, okay. Now, let us look at mole balance for a species A, let us just call species A, okay. What would be the molar flow in? So, this is a well mixed reactor. So, that means if you look at this point versus this point versus this point versus this point, the conditions are exactly the same, okay. If there is outlet, then the condition at this point is also exactly the same, okay. That is the meaning of well mixed. What is the molar flow in? We will just write this as Ca. Yeah, what is the molar flow in? F in or F A in, okay. If you are given volumetric flow in, then if Q in is the volumetric flow rate in, Q in multiplied by Ca in, okay. Molar flow out, Fa out Ca, okay. I am just writing this as Ca because concentration of out is equal to concentration within the entire reactor. What is the rate of generation? RAV, capital RAV, okay. Do not have to worry about anything else because by sign convention we have said capital R is rate of formation or rate of generation because of reaction. If that value is negative, it is a reactant, if the value is positive, it is a product, okay. Nu multiplied by rate of reaction will handle all of that, okay. Nothing, no, small RA is your undergraduate, right. Small RA, I hope you have forgotten 15 minutes before earlier. When I wrote this, thereafter I do not want to touch small RA, okay. Not that small RA is invalid, not at all, okay, it is not invalid. Small RA is valid under an assumption that A was equal to 1 or A was equal to -1, okay. So, that is why, I mean, why bring in one more when XYZ into the picture. So, I am just not going to talk about small RA, we can always talk about small RA after the class, okay. And you have confusion, you bring it up in the sheets that I am going to start circulating once a week, okay. So, it is a perfectly valid question, It's just that to avoid confusion we are just moving on, because then small RA, I don't know if you remember, at least in my undergraduate I used to always think there should be minus, there should be plus, I don't know whether it should be divided by minus RA, it should be divided by plus RA, I don't want all of that, okay. Small r, if it is plus, reaction is going from left to right, minus your reaction is going from right to left. Capital R, value is positive if R is being with that species is being formed, value is negative if that species is being consumed. We are not going to call it reactant, product and all that, species being consumed, species being formed because of myriad number of reactions, because a particular species can be a reactant in a reaction, but it can be a product in another reaction. Why not ourselves in those definitions which are beyond a certain point and not beneficial. Okay. So, if we write accumulation, okay, what is rate of accumulation? D by dt multiplied by the intensive quantity. What is the intensive quantity when it comes to mole balance? Total number of moles. What is equal to the total number of moles? What is the mathematical expression for total number of moles? Ca into V. Okay. And if there are n number of species, okay, this is essentially how we are going to write it. And this rate of generation is just going to use summation mu kj rj. If it is a single reaction where your reaction is written as A plus B by AB giving C by A C plus D by AD, that is the special case that amounts to the minus small ra terminology, okay. But let us not worry about that, okay. And this is essentially what we are going to get, okay. This is valid for a batch reactor, valid for a semi-batch reactor, valid for CSTR, it is valid for all well mixed reactors. In batch reactors there is no in and out, so you have dN by dt equal to RV. In CSTR, that is at steady state, d by dt is 0, that is the definition of steady state. Steady state means things do not change with time, things do not change with time means d by dt equal to 0, okay. So, the left hand side becomes 0, so 0 equal to Fn minus Fout plus Rv, that is your CSTR, and same then with batch reactor, and based on that we get all of these design equations and so on, okay. Next lecture we are basically going to start at this point, okay. First 20 minutes or so, first 20-25 minutes we are going to cover the CSTR and PFR and so on, okay. Thereafter I am going to move on to some math concepts. That is what I am going to do in the next lecture. All of this is already uploaded on your Google Drive, https bit.ly bit.ly/ch5010, c small h small 5010, no backslash. And Usually if you use Chrome or Firefox, you do not need to add the HTTPS, it automatically adds it for you. So, bit.ly/ch5010, the unannotated material is already there. Okay. Please read ahead, especially the math things. There are not too many of math stuff that I have, but please read ahead so that we can finish this off quickly in the next lecture.